Okay guys, so let's get started. So the overview was already given. So today we'll get started on module 1, and module 1 and as I already illustrated that there are going to be 4 modules in this course. In module 1 there are 3 things that we need to be taken care of. The first one is on the overview of classical models, overview of, I'll say, general old classical AI. The second topic in this module is more focused on neural networks, and this will include some various forms of deep learning. And the third topic in module 1 is on the ML risk overview. So what I'll try to do is I'll try to put this in one single video of say 30-40 minutes, and I'll try to put both of them in the second video of another 30-40 minutes. I don't want to put everything in a single video because the length of the video will become very large. So as I have already illustrated that the primary purpose of this course is that AI is in the epicenter, and then we'll keep talking about the risks that are related with AI, the governance and the the regulatory stuff and the ethical considerations, etc. Okay, so AI is the core of the entire course. So whether you are a business user or whether you are somebody who is not so familiar with AI, you will you don't have a choice rather than to get into some of these details. Okay, I'll still try to keep this not too intense on the mathematics, but there would be some amount of math that is absolutely necessary. Okay, so now let me get started. So we'll start with some kind of a timeline view of computer science and AI. So if we go deep back into the history, say close to say I think 1837, that's the time when the first mechanical computer came into existence. So there was a person called as Charles Babbage, and if you go through some of these courses on computer science, he is still considered as the founding fathers of computer science. So Charles Babbage, he created a computing machine which was more of a mechanical computing machine. However, there was some amount of automation in some amount of the arithmetic computations that were happening. So Charles Babbage was the first guy who said that all of this is possible to compute. A little after this, in 1843, there was a lady, her name was Lady Lovelace, and she is considered to be the first programmer. Okay, so on all of this mechanical computing machine, she was able to write some programs, not the programs as we see them today, but some kind of non natural language code which could execute the instructions on these kinds of mechanical devices. So all of this happened in 1843, and then I think after quite a while, in the start of 1900 or 1906, the first triode was invented, and kind of an electronic device which created the foundation of all the complex electronic machines the way we see them today. So that was in 1906, and the next milestone, the larger milestone, was in 1936, if I remember correctly, and this was by Alan Turing. So Alan Turing is one of the very respected person in the field of computer science, in the field of algorithms, in the field of anything that we do, the data structures and algorithms. He was the first one who created something called as a Turing machine. You may know the Turing machine already, or you may not know. And so Turing machine was the first theoretical framework which laid the foundation that any kind of a problem, whether it is arithmetic problem or a logical problem, can be solved by Turing machine, which is, I will not get into the details of the Turing machine because otherwise the length of the video will become very large, but you can read. It's a very interesting topic on Turing machines, and Alan Turing was such a kind of an intellectual person in UK who created this Turing machine. Then there in 1956 there was a person called as McCarthy, and he coined the term of artificial intelligence. So McCarthy is considered to be, you can say, as the founder of AI, or he for the first time the term was used by McCarthy in 1956. And all of this history and timeline is a part of the course, is a part of this RAI course, and there is a likelihood that you may get some questions around this as well. So this is important. Then the next big thing that happened was in 1964 when IBM came with an electronic computing machine called as mainframe. We still use mainframe in many organizations. Mainframes were like large computing machines which could process a lot of instructions. After that, a lot of other things would have happened, but let me say, and I'll get into the nitty-gritties of some of the latest things now, because a lot, if you look at on the left hand side, the developments were very sparse, but as we come on the right hand side, the developments will become more and more more and more close to each other. So in 1980s, IBM and Microsoft, they came up with these personal PCs, some of these softwares like Microsoft Word, etc. So this is when the computers were commoditized or democratized, and somewhere in 1989, I would say, the internet was also present. Now if we want to go into a little more detail on the developments that have happened in the recent past, then I would say that let's focus on the developments that are more on these lines of AI and machine learning and neural nets and those kinds of things. So we can start with probably 1960, when your neural networks were first conceptualized theoretically, and then 1986 the backpropagation paper was published, 1995, and these are some of the mentions that are there in the course. I can get into more things that happened in between, but I'm not going to go through all of those things because otherwise it's only going to confuse you. 1995 LSTMs came into existence, and then probably around let's cut short this to 2020, when your the first versions of GPT-3 came into existence. And so 2022, this is where the ChatGPT took the world by a storm, and some of the other fun things like stable diffusion, etc., etc., also came into existence. 2023 was the year of all of this has already taken the world by the storm. So people started talking about explainability and those kinds of thing, and there is something called as neuro symbolic AI, where you try to combine the neural networks with some kind of an interpretability and build systems which are also easy to understand. 2024 is the year when we started talking about the regulatory aspects of AI, or you can say AI governance, along with some initial work on quantum computing in relationship with AI, etc. So this is the timeline that is there with respect to the developments that happened in the field of AI. Now, having said this, now let's get into some of the other specific sides of AI. So let me start with the specific AI. And then we'll get into more general purpose AI. Most of our classical AI is specific AI. So when I say specific AI, there are systems that are developed to solve a particular problem, to play chess, to play a game of NIM, or to solve some other kind of a problem. In the general purpose AI, this is more modern AI, where systems like ChatGPT are able to solve problems related to multiple domains. But your classical AI is more of a specific AI. And then the third step is a lot of people talks about AGI, which is artificial general intelligence, which will have all the it will not even need the inputs from humans, so it will be more autonomous and make decisions on their own behalf, which is still very futuristic. We are somewhere in between both of them, where we are talking about agentic AI and those kinds of things, but still far from AGI. So the first topic that you need to understand as a part of our AI course is some foundational stuff on reinforcement learning. So if you already are aware, machine learning generally is divided into supervised, unsupervised, semi-supervised, and reinforcement. So reinforcement learning is kind of a very, very interesting learning, where you perform an activity. So when I say an activity is nothing that you are in a state S, you do some activity A, you reach to state S dash, and then you keep doing this, you keep do activity A dash, and then you reach S dash dash. So eventually you will find your end of all of these states. And let's suppose we are talking about say a chess game. So you play your turn and you get into another state, the opponent plays his or her turn, and then it gets into another state, and finally there is a final where either it is a win, either it is a loss, or it is a draw. So what reinforcement learning does is that it keeps track of all these states and actions, and whatever is the end, it will try to learn from the end state and then back propagate the learnings to all these states and actions, so that a more brute force kind of an learning is applied, which tells me that if I am in state Si, what could be the most appropriate action A to increase the probability of winning in the end. So let's take an example. There is a game is called the game of Nim. And what happens in this game is there are 20 coins and the opponents play one by one. Each opponent is allowed to either take away 1 coin, 2 coin or 3 coins. So the opponent has to take away either 1 coin, 2 coin or 3 coins, and the person who picks the last coin, he wins. Okay, so if you think like a human, you would understand that in the last turn, if you really want to win, you should have either 1 coin or 2 coin or 3 coin, because if you have this kind of a combination in the end, you can either pick all 3 of them, 2 of them or 1 of them, and you would win. Which means that in the n-1 last turn, you should have 4 coins, or your opponent should be left with this kind of a state where there are 4 coins on the table and it is his turn, because even if he picks 1, 2 or 3 coins, it is going to take you to this state. So that's how a human mind works. But how would a reinforcement learning do this is that we'll put all these pictures of, say, coin. This is the first coin, this is the second coin, third coin, fourth coin, and so on and so forth. Let's suppose this is a 19th coin, this is 20th coin. So these are your 20 coins, and then we'll put, let's put data structures which has 3 placeholders for each state, and so this is to remove 1 coin, this is to remove 2 coin, and this is to remove 3 coins. So let's say these are some kind of probability distributions or number. Just to make it simple, let's keep this between 0 to 9, 0 to 9, because if we do fractional stuff right now, it will make things complex. So what reinforcement learning would do is, it will, let's suppose, initialize all these numbers as 5. So 5 means that there is an equally likelihood of picking up any of these, and if there is an equal likelihood, it can make a random guess. So it will do all of this stuff and play a few games, either with a human or play a few games with computer itself. And we would see that after a few hundreds of iterations, it will find out an optimized way that what would be the the best optimized way for each of these states, each of these 20 states. So as I was telling you that I think it is very easy to think that for the 1 coin and 2 coins and 3 coins, it should be like this. If there is a 1 coin, it should be 900. If there are 2 coins, it should be 090. If there are 3 coins, it should be 009. So which means that if there are 3 coins left on the table, you need to pick 3 coins. If there are 2 coins left on the table, pick 2 coins, and that's how you win in the end. So you will find that this kind of matrix is created after, say, 100 iterations or so, and this is what reinforcement learning exactly means. Okay, so after every win, what happens that all these random states, or all these let's suppose when the numbers were initialized randomly, computer picked this one, and then 2 coins were, or it should be done from right to left. So when there were, say, 20 coins on the table, the computer thought I should take the 1 coin, which means there were 19 coins on the table now, and then the opponent took 2 coins, which means that state 18 will not there, 17 will happen, and then on the 17 the computer again picks up 3 coins, etc., etc. So if those kinds of actions were taken by the computer, and let's suppose in the end the computer wins and the human loses, then all the turns where the computer made the choice, those will be increased by say +1. It can be some other incremental stuff also, which is the kind of a learning rate, but let's assume it will be increased by 1. So this 5 will become 6, and if this has to becomes and let's say all of these will become 5 only. So this will increase by 1, and all the turns that were taken by the other computer or the other human being, which eventually led to the loss of that particular player, that will be decreased by 1. So this will become 4, etc, etc. So this is how the numbers will be updated, or the weights will be updated, eventually reaching to a conclusive matrix where the machine would have learned what is the right way to play this. So this is on a high level, this is what is reinforcement learning. We'll also get into the details of reinforcement learning in module 2 when we discuss this in more detail, but this is enough for the first module, where we just touch upon some of these concepts. The second topic after reinforcement learning that is important as a part of the first module is something called as a look ahead. So look ahead means that there needs to be some intuition of looking into the future. So what we saw here in this game of NIM is that we were only concerned about what we are playing now, and just back propagating or updating the weights based on whether we win or lose. There is no intuition of what is going to happen in future, and we are not even concerned if my turn now, if I'm removing one coin, how is it going to possibly impact some of my future states. So all of that is not happening here in this particular example. But imagine if you are solving a Sudoku, or if you are solving the game of the Tower of Hanoi. You have to be aware of what your current action is going to play an impact on some of the future events. For example, in case of a Sudoku, if it's a numerical Sudoku, let's suppose, and you put number 7 somewhere, it means that you cannot put number 7 in the same row or same column or same diagonal if the diagonals are also constrained. So those kinds of futuristic or look ahead constraints needs to be taken care of. And if I am not allowed to put number 7 here on the same column or same row, how would it impact some of my constraints in that same column or same row, etc, etc. Similarly, in the Tower of Hanoi, when there are 3 towers and there are discs that are put in the increasing order of size, and you have to move these discs from say Tower A to Tower C, using some form of Tower B as well. If you need to do so, you need to be very cognizant that if I am keeping my smallest plate here, and if I put the second biggest here, how is it going to impact the arrangement of some of these other plates? So that's something called as look ahead, which needs to be taken care of in some of the problems which needs to be solved. Just extending this look ahead, then there is something called as more of adversarial look ahead or heuristic look ahead, which is an enhanced thing of look ahead. And after look ahead, there are also a concept called as search in AI, in algorithms, in computer science at larger. So what search means is that so let's start with something very, very basic. If there is a bunch of numbers, let's suppose there is number 7, 16, 3, 4 and 21. If I need to find a number from this possible set of numbers, the brute force is sequential search. So sequential search means that if I have to find the number 4, I will go here, I'll go here, I'll go here, and I'll come here and then I'll find the number 4. Whether I need to give the index or just true and false, it can take me possibly n times if the number is in the end. So that's the sequential search. A slightly more sophisticated or advanced search is something called as a binary search, where while we are creating this kind of a list, we make sure that the numbers are in the ascending order. Okay, so it is going to be 3, 4, 7, 16 and 21. Now when we want to search for number 4, we go and hit in the middle and we see whether this is the right number. No. Is it smaller than this number? It is larger than this number. If it is smaller than this number, we only need to search this list now. And if it is larger, we need to search on the other side. Then we go and hit the middle one and we see, is this the right number? And it is the right number. Okay, so we will find it in possibly 2 tries rather than say 5 tries. 2 is in this case, but even in the worst case, it takes log to base 2 of the number of elements in that particular array or anything that we are saying. So that's called the binary search, which is a more sophisticated search or a more advanced search. And then there are some searches related to say, let's call them as a tree search, which is something that most of your machine learning and AI algorithms will consume or will use at some point of time. So what happens in tree search is that if you are in some state and you need, let's suppose this is a map problem where if I am in Pune and if I need to, let's suppose, go to Bangalore, what are some of the possible routes which I can take? So I can go to Mumbai. From Mumbai, I can do some hops and then go to Bangalore. I can go from Pune to say Satara, and that's how. Or I can probably become more enthusiastic and go to Delhi first and then come here, etc., etc. Okay, so if this is a kind of a problem, if it's a kind of a tree search problem, there can be multiple methods by which we can solve this kind of a search problem. So there are things like a breadth first search, where as the name suggests, you go widthwise. So you will say, okay, from Pune to Mumbai is 200 kilometers. If your distance is your utility or kind of an cost function, or time is the cost function, or your dollar value is a cost function, depending upon that you keep track of how much it cost me from Pune to Mumbai. Let's suppose it cost me 3,000 rupees if I take a cab from Pune to Mumbai, etc., etc. And Pune to Satara is, let's suppose, 2,000, and Pune to Delhi is a flight which is 6,000, etc., etc. So depending upon what metric you want to see, BFS takes care of keeping a track of that metric width by width, and then once you are done with say first pass, it will go to the second pass, etc., etc. The problem with BFS is that it is very, very inefficient in terms of memory. Okay, so if you have, let's suppose your branching factor is let's suppose k, then in your first pass you will have k things to be remembered in your first pass. In your second pass it is going to be k multiplied by k or k square, because each of these bunch or each of these places will have multiple options again. So BFS becomes very, very inefficient with respect to memory, because you need to keep track of so many things. There is another approach which is called as DFS, which is called as a depth first search, where you try to take one branch first and go till the end and find out if it is the optimized way to do this, and for which again you'll have to do the second branch, third branch, till or you end up with all the options. The problem with DFS is, while this is efficient with respect to memory because you don't have to keep track of all the routes, but it is inefficient with respect to time. It takes a hell lot of time to find out all these possible options. And so there is something in between which is called as A star or more heuristic search, where what happens, you go from state 1 to state 2, and you also have some kind of an estimate that if the bare minimum from state 2 to state end is going to cost me, say, C dash. So if this is C and if this is C dash, your total cost is going to be C plus C dash. So you have some kind of an estimate. In case of, let's suppose, if distance is my metric, I can say that, okay, maybe C dash is, or my heuristic is your crow flight distance. So crow flight distance is nothing but between the two. Let's suppose we are talking about 2 dimensions. It is the square root of these squares of the x and y coordinates. So if this is Pune, and if this is Delhi, and this is Mumbai, and this is Bangalore, so the minute I go from Pune to Delhi, the crow flight distance of Delhi to Bangalore is going to be much worse than Pune to Mumbai. So this option anyway will be discarded in the immediate first pass itself. So these kinds of heuristic search will give you more optimized methods to parse a tree or to parse all the possible options to reach to your end goal. So these are some of the search techniques that you need to know. You may be asked a little bit about some of these things in the exam. The next topic that is important is, and I'll try to finish some of these topics and then close this video faster, is something called as recursion. And if you have a computer science background, most of these concepts should not be alien to you. These should be very, very simple to comprehend. So recursion is also something that when you try to solve a problem, so if you try to solve a problem for, say, n, we should be able to solutionize this algorithm for n factor in some kind of a function of solution of n minus k. So if I am able to formulate my algorithm in such a manner that the solution for n terms or n size is a function of the solution of some smaller value of n, this kind of an treatment to solve a problem is called recursion. There is one more condition that needs to be satisfied here. In this case is the solution for, say, 0 or 1 or some other grounding needs to be finite and more like hard coded. So let's suppose if I need to find out the Fibonacci for, say, n, it is nothing but some form of a function of Fibonacci of n minus 1. And this is one of the examples which everybody will take, that if the Fibonacci series, if you want to solve or if you want to list all the Fibonacci series 0, 1, 1, 2, 3, 5, 8, etc., etc., this is nothing but addition of these two. So Fibonacci of n minus 1 is nothing but the the sum of the last two numbers, and which again can become another function of n minus 1, n minus 2, etc., so on and so forth. And Fibonacci of 0 is 0, 1 is 1. So that's the recursion. That is how most of your machine learning algorithms will use recursion for. The next term is more on the the adversarial tree search. which is also a tree search but more adversarial. When I say adversarial, it needs to be familiar with some kind of a cost function, or so let's take an example. Let's suppose you want to play a tic-tac-toe, and let's suppose I have made this move. Now my partner or my opponent needs to make a move. And now in this particular case, each of these boxes will have some kind of an objective function, or let's suppose I define the objective function which is minimize the opponent's probability to win and maximize self probability to win. Okay, so in a tic-tac-toe you need to have your three markers on the same row or same column or same diagonal. So based on this objective function, each of these boxes will calculate some values, say a numerical value, and whether it is a maximizing function or a minimizing function, your opponent is going to play something. And then again, you also run a similar optimizing function, and you say, okay, now I would play this, and then your opponent plays this, and then you play this, and then you are definite to win. So at the end of the day, you run your algorithm, you find your optimization function across all the possible open spaces in this case, and then accordingly decide. This is the example of adversarial search tree. However, the problem in this case is, in case of a tic-tac-toe, there are only 9 states, which also keeps diminishing as you keep putting your markers, and it eventually goes to 0. But if you play a more complex game, say like a game of chess or even a game of checkers, the options becomes larger, which means that it is almost impossible to compute all of these things in all the permutations and combinations. Also because not all your pawns or all your things that are on the table carry the same value. So there will be king, there will be bishop, there will be a rook, and all of these will have their own directions of moving, own importance, etc., etc. So as your games become more and more complex, it is almost impossible to apply this kind of an adversarial tree search, and that's where some of these old-fashioned AI comes to a standstill. It can solve smaller problems, but it often reaches a peak where it is almost impossible to solve some of these larger problems. Okay, and that's where we come up with some of these other neural networks, or some of the more complex ways of, or more heuristic methods of solving some of these larger games, which may have objective function like a material balance. So if you have more number of your pieces on the table, especially in a game of checkers, you are much better off. Or you can have some kind of a positional balance. So positional balance means that in a game of chess, if your pawns or your material is in the middle of the game, it is much better rather than having it in your side of stuff. So that's the positional balance. It can also have some kind of a look ahead balance, which means that your material balance might be very, very less. You have 2 pawns here which are, say, 2 points, and your opponent has a rook here and a bishop here. So 5 plus, say, 3 or 4, whatever you want to consider it, is 8. But then once you take this to the last position, you can have a queen here. Okay, so that's something what is a look ahead balance. So some of these old-fashioned AI will use a lot of heuristic stuff to solve the problems which are more complex or more compute intensive to be solved by just using an heuristic tree search. So the last topic in module 1 module 1 topic 1 is some of the key limitations. We already discussed this till now, but limitations of old classic AI. And this is a small topic which is 1 page in the end, and it talks about as in early 60s and 70s, when AI was more heuristic or more search driven, and there were languages like Prolog, which is programming logic, where inventories of rules were created, and those inventories of rules were inferred to solutionize some of these games or other stuff. So there is a maximum limit to which all of these inventories can be created. There was a project called as CYC, if I remember this correctly, and I think it was done by Douglas Lent, and by 2017 or so, we had consumed 1000 person years of effort to build an inventory of the rules, or of all the general knowledge or information that could have been put into this kind of a CYC ontology. So having these rule based and adversarial and search based thing, it can reach to a maxima. The second problem which we talk about is that all the examples that we have taken are more discrete. When I say discrete, either it's a win or a loss, or I can take 1 coin, 2 coin and 3 coin. There is very less probabilistic means of evaluation. I can be in a state S, and then my next state can be in between 2 states. I most of my old-fashioned AI is more discrete rather than probabilistic, which is because as we get into more continuous forms of distributions, the compute and the resources required will also increase exponentially, which was the problem with some of this old-fashioned AI. So these are some of the limitations, and as we get into our next topic of deep learning, we will find that how deep learning was a boon to solve some of these more complex problems, how it was able to construct or estimate a function which is a non-linear function, functions which can be order of magnitude complex than what some of these searches will be able to take you through. And then there are so many forms of deep learnings, whether it is CNNs or LSTMs. So we'll get into details of that in the next video. And then the third part of module 1, which is the last part of module 1, is on the risks of overview of risks, which can be on a high level. We'll say what kind of risks we can get into with the advent of AI making decisions. So thank you so much, and I'll see you in the next video.